Let's take a look now at section 15.8, and let's talk about Stoke's theorem. Stoke's theorem is a generalization of Green's theorem into a higher level of dimensions. However, once we define it and once we illustrate it, you'll see how it is just a generalization of what we've already seen. Let S be a surface oriented by a unit normal vector that is bounded by a piecewise smooth simple curve C that is oriented clockwise relative to n. All right, so before we continue, let's illustrate that part. You have a surface. Let's go ahead and draw this. Here's my surface. Okay. It's oriented by a unit normal vector. So here I'm going to say, here's my unit normal vector. It doesn't have to be a unit normal in any particular direction, although we often consider the up direction the one we want. We consider the n as the normal vector, and this surface is bounded by a piecewise smooth curve called C. Notice that's just this outer boundary, the outer lip of this surface. So here, this is the boundary of this surface. We're going to call that C. So this is our S, this is our N, and this is our C. C is oriented, that should be counterclockwise. C should be oriented, that should be counterclockwise relative to n. What that means is, if you were staring from this direction, if you were standing up here and looking down, you should see this rotating counterclockwise. Another way of doing this is with what's called the right-hand rule. Imagine that you're grabbing this. Imagine this is a physical cup. All right. So, for example, something like this, just a little cup. All right. All right. So here's your object. Imagine that you're holding on to it this way here, and now imagine that your thumb is the unit normal vector pointed upwards, or really in any direction. Yeah, I can see myself. Hello. So notice that your fingers curl in this direction. All right. So if your thumb is pointed that way, the way your fingers curl, that is the the counterclockwise orientation. Okay? Here, it doesn't have to be up. If you pointed downwards, that would be fine too, but then your fingers would curl in the opposite direction. So here, it doesn't matter which way you're pointed. Rather, what matters is the relative position between the unit normal vector and the rotation around this way. So here, if that's n, the way your fingers rotate, that's the counterclockwise orientation that we want. And of course, that counterclockwise orientation is around this bottom edge, this bottom lip of this surface. All right. So that's what we have here. We have S is a surface oriented by a unit normal vector, whatever way it's pointed. Here I've drawn it up, but it can be in any direction. That surface is bounded by a smooth, simple closed curve that's oriented counterclockwise, as we've drawn here, relative to n. If n changes, so does this. All right. Let F be a vector field. Okay, so this is sitting within a vector field, and the components of the vector field have continuous first partial derivatives in an open region. So every point on this surface and this curve, for every point on the surface and the curve, it's true that you have a continuous first partial. Right. So if all of those things are true, then the line integral around this curve C of f dot dr, as we saw in chapters 15.2 and 15.3 when we defined line integrals, that line integral is equal to the double integral, is equal to the, with respect to the surface area, not of f dot n ds, but of the curl of f dot n ds. So it's not sufficient to have f here, it's going to be the curl of f. All right. The proof of this is extremely complex. It's the kind of proof where to go all the way through this, we would spend an entire semester just on that proof, just on developing the material necessary here. So here proof is omitted due to complexity. It's just not something we can realistically do right now. complexity. That said, you saw a very tiny part of that proof. If you go back to section 15.4 when we discussed Green's theorem, we noted that an alternative version of Green's theorem, it involved the line integral around a closed contour C of f dot dr. It equal to a double integral over a region of the third component of the curl. So that is one small piece. Here it was this equals to double integral over r of the third component of the curl of f dA. So that is one very small component of the overall proof. Here we're not going to prove it, although it is related to that previous alternate form of Green's theorem. Note here that this actually is very reminiscent to Green's theorem, which stated that if you have a solid disk, or really any solid region in the xy plane, we call that R, and you had a counterclockwise oriented boundary to R, right? Then you could say everything about what's going on the inside by looking at what happens on the boundary, or vice versa. Namely, you had that the line integral, this was your curve C, you had that the line integral over C of f dot dr was equal to the double integral over that region R of del n del x minus del m del y dA. All right. Note that that's one component of the curl. This is the third component of the curl of f, where f is given by m comma n comma p. So here you're saying something about a line integral, but instead of saying it on a flat region and that contour is surrounding that region, now you're saying it on a surface, and that curve is a boundary of that surface. So in a way, Green's theorem is just a special case of Stoke's theorem. So at any rate, here, let's go ahead and take a look at some examples of using Green's theorem. Yeah? Sorry, of using Stoke's theorem. So for example, let's go ahead and take, let's find the line integral over C of f dot dr, where f is the vector field given by 4xz comma y comma 4xy, and where s, the surface S, is given by z equals 9 minus x squared minus y squared. Okay. Here we're going to say, that we're told z is greater than or equal to 0. We only want the upper part of this paraboloid. Here we're also told that C is the boundary of S, oriented counterclockwise when viewed from above. Okay. All right, and that just confirms that we're looking at something that is oriented in the correct direction. If it was ever not oriented in the correct direction, of course, we could always take the other normal vector. All right, if pointing up has us facing the wrong direction, then pointing down will now have you facing the correct direction. So you can always change which normal vector you're using. Right? But here, everything works out nicely. It's counterclockwise viewed from above, so everything works out the same way here. If not, instead of using n, you would use minus n. Okay, so let's see here. We're looking for the line integral over C of f dot dr, which by Stoke's theorem is the double integral over S of the curl of f dot n ds. Note this is still a flux integral, right? Except instead of using f as your vector, you're using the curl of f as your vector. So this is still going to be computed the same way we compute a flux integral, which means we can use from 15.6, here, let me write that. by techniques from section 15.6, we can now write that as the double integral over R of the curl of f dot n, which is the curl of f dot, here that's going to be g sub x comma g sub y comma 1. Although I guess since we want the upward oriented vector, this would be minus g of x comma minus g sub y comma 1. If we had that oriented in the opposite direction, if that was supposed to be minus n, then that would be positive, positive, and negative, right? dA. Okay, so now we just have to find all these components and pop them all in. And you say, well, we don't have a g. Oh, sure we do. That's this thing right here. So here we're going to say that's our g of x comma y. Which means that our g sub x is simply the derivative of this with respect to x. Right? Note, if this was not z equals to something, you would have to isolate z first, since g is a function of only x and y. But since that is already a function of x and y, here the derivative with respect to x is minus 2x, and the derivative with respect to y is minus 2y. Okay? So that gives me these. And so I can write that as the double integral over R of the curl of f dot, let's see here, that's the negative of 2x, right? Negative of a negative, that's positive 2x. Negative of a negative, that's positive 2y, and that's 1, dA. Okay. Next thing we need is the curl of f. Okay, and we've seen the curl of f computed before. Let's go ahead and do that now. Let's see here, f is given by 4xz comma y comma 4xy, then the curl of f is often written as the differential operator crossed with f, which in spite of that terrible abuse of notation, it is a wonderful mnemonic. It's a good way to help you remember that. And that's going to be what? Del x, del y, and del z, the differential operator. And then the components of f, that's going to be 4xz, y, and 4xy. Just like that. So now, let's see, that's going to be the derivative of 4xy with respect to y. That's just going to be 4xi. Plus the derivative with respect to z of 4xz. Well, that's going to be 4x as well there. And if I take the derivative with respect to x of y, well, that's a constant with respect to x, so that derivative is going to be 0. Minus, going back this way, with respect to z, y is a constant, so its derivative is 0. With respect to x, the derivative of 4xy is just 4y. And with respect to y, the derivative of 4xz, well, 4xz is a constant with respect to y, so that derivative would just be 0. And so if I subtract these off, that's going to give me the curl is going to be 4x minus 0, so that's 4x, comma 4x minus 4y, comma 0 minus 0 is going to stay 0. So there's the curl of f. So that means that our line integral over c of f dot dr is going to equal to the double integral over r of, we left off on the last page by saying that we wanted the double integral over r of the curl of f dotted with 2x comma 2y comma 1. 2x comma 2y comma 1. Oh yeah, but we just found the curl of f, so you can plop that in. That's going to be 4x comma 4x minus 4y comma 0. And so that's going to be the double integral over r. Let's see, 4x times 2x is going to be 8x squared. 4x minus 4y times 2y, that's going to be plus 8xy minus 8y squared. And then that's going to be 0 times 1, which is just 0, so we can ignore that dA. All right. So now the last thing is we're going to need to find the boundaries of R so we can integrate. Remember what R is. Assuming we're looking at a surface S, R is simply the projection of S onto the xy plane. So here, the surface that we have is z equals to 9 minus x squared minus y squared. So if you're going to project this onto the xy plane, what you're looking at is, this is a paraboloid. But if you're trying to project this onto the xy plane, well then z would be 0. Right? This continues to grow outwards as you move toward the plane. Its maximum height is when x and y are both 0. This would be 9. And then this would simply be a paraboloid facing down because both of these components are negative. So the projection of this, right, we only want the upper part, onto the xy plane, well, that's simply going to be the place where this paraboloid intersects the xy plane. So here, this is our R, which if we want to draw just that part, notice that's just a circle. Here, when z is equal to 0, that's going to be x squared plus y squared is equal to 9. Or in other words, that's just the circle of radius 3. That R is the projection of this surface onto the xy plane, which is the circle of radius 3. All right, so here, that's the circle of radius 3. Oops, or radius 3, of radius 3. Centered at 0, 0. Okay. All right, well, I note that my region is a circle, and I notice I have sums and differences of squares, and that really suggests I want to use polar coordinates. Anytime I have squares and square operators and circular regions, polar is probably the better way to go. Before I started this, I actually did it both ways, and I tried to do it both ways. I gave up halfway through the rectangular one. It was doable. It's just very, very unpleasant looking. Polar is certainly a lot better for anything like this. So let's go ahead and give that a try. Converting into polar, that's going to equal to the double integral. All right. Well, now we're going to use an iterated integral. Here, 8x. Well, in fact, I noticed that 8 is a common factor, so let me just pop that out from the very beginning. My x squared is going to be r squared cosine squared of theta. My x times y, that's going to be r sine of theta times r cosine of theta, which is going to be r times r gives me r squared cosine of theta sine of theta. All right. And then here, I've got the minus. The 8's already been factored out. Y squared is going to be r squared sine squared of theta. And then dA in polar coordinates is going to be r dr d theta. Our value of r for a circle of radius 3, well, r is going to go from 0 to 3, right, from the pole out to the circle of radius 3. And since we want the full circle, we didn't have any restrictions like in the first octant or anything like that, then that means we're going to want the full revolution, so theta will go from 0 to 2 pi. Okay. Here I notice I have r squared as a common factor, so let me factor that out. And in fact, I have another r to join with it, so this will give me 8 times the integral from 0 to 2 pi of the integral from 0 to 3 of r to the third times cosine squared of theta plus cosine of theta sine of theta minus sine squared of theta dr d theta. With respect to this first integral, with respect to r, this whole thing's constant, which is nice because the antiderivative of a constant times r to the third is that same constant times r to the fourth over 4. So here we can write this as 8 integral from 0 to 2 pi of r to the 4th over 4 times the cosine squared of theta plus the cosine of theta sine of theta minus sine squared of theta, where r is being evaluated from 0 up to 3, like that. Obviously, if we substitute in 0, that whole thing is 0, so we don't worry about it. But if we substitute in r equals to 3, we're going to get 3 to the 4th is 81 over 4. If we multiply that by that 8 out here, 81 over 4 times 8 is going to become 162. So that's going to be 162. All right. The 0 doesn't do anything. Plugging in a 3 here gets you a fraction. But since that's a constant, you can factor it out times the 8. Will give you 162 times the integral from 0 to 2 pi of cosine squared of theta minus sine squared of theta plus cosine of theta sine of theta d theta. You might notice I brought this one over here. I just had those switch places, right? Negative sine squared of theta and then plus sine of theta cosine of theta. There's no reason that you have to do that, but I recognize that I can do this integral just slightly more simply if I use a power reduction formula here. One thing I could do is I could use the power reduction formula on this one on its own and this one on its own, and then factor out the 2's from there, and then distribute and then combine like terms and then integrate. Or, a little more simply, I recognize that this thing right here is the double angle formula of cosine. Double angle formula for cosine. Basic trigonometry makes life easier, especially when you're dealing with trigonometric functions in the first place. Here, this is almost the double angle formula for sine, except the double angle formula for sine usually has a 2 right here. Oh, okay, well then that's just going to be half of the double angle formula. So this is the double angle formula for sine. Oh, but it's missing the 2 there. Okay, so it's been cut in half. So it's going to be 1/2 times the double angle formula for sine. So here I can write this as 162 times the integral from 0 to 2 pi of, this is going to be cosine of 2 theta. No more powers, makes things a little nicer and easier. And here, this is going to be plus 1/2, and that's the sine of 2 theta. That's what we mean by a double angle. Oops. Just like that. But now each of those integrals is readily accessible. This is going to be 162. The integral of cosine of 2 theta is sine of 2 theta. Oh yeah, but because of the chain rule, I'm going to have to multiply by 1/2. Plus 1/2. The integral of the sine of 2 theta is negative the cosine of 2 theta. So let me put my negative in front. Cosine of 2 theta. But now, again, because of the chain rule, I'm going to have to divide the whole thing by 2. I'll multiply by 1/2. And now that evaluates from theta equals to 0 up to theta is equal to 2 pi. All right, so let's see. We can clean that up a bit. Let's see, that's going to be half of, let me distribute this number here. So 162, let me just go ahead and plug in the numbers right here, right as it is. 162 times 1/2 the sine of 2 theta minus 1/4 the cosine of 2 theta. And here theta is going from 0 up to 2 pi. All right, so let's see what that's going to give us. That's going to be 162 times, if I plug in 2 pi right here, the sine of 4 pi is 0, minus the cosine of 4 pi, that's 1, times a negative 1/4. Okay, so that's 0 minus 1/4. Minus, now if I plug in 0, the sine of 0 is also 0, minus 1/4 times the cosine of 0 is 1. Okay, so negative a fourth times 1 is negative a fourth. And here, this number minus itself is 0. So in a rather anticlimactic end, our result is 0. So that means that our line integral f dot dr is 0. This is a rather convenient way of computing a line integral, particularly in those cases when you have boundaries which have to be parameterized separately. We've seen cases where, you have to parameterize your boundary, and your boundary looks something like this. And now you have to parameterize each of those lines on its own, and that's just a pain. Not that it can't be done, it's just annoying to do. But instead of dealing with each individual parameterization, in order to add them all up to give us a line integral, instead what we can do is we can deal with the same vector field, but instead of dealing with it on its own, we take its curl and then take a double integral over a surface. You might say, well, how do I know what surface? If I was given a curve, how do I know what surface? It turns out any of them. As long as your surface is oriented by that normal vector, which makes this counterclockwise or relative to that normal vector, and as long as f has components that have continuous first partial derivatives, then it's fine. Here, if I had used this paraboloid to give me this counterclockwise region, I could have used a completely different paraboloid, or I could have used a sphere, or I could have used a cylinder. I could have used any shape. As long as it still gave me this curve, then the integral over the curve would have given me the same result of 0 no matter which surface I used. Right? So that's one of the nice things about this. If your contour is unpleasant, all you have to do is find some nice surface that has that contour as its boundary and use that surface instead. Okay. Now let's give just a quick illustration as to what all this stuff means. In several other sections, we've had notation, and we've had notation that tells us here we're taking a double integral. Oh, and by the way, here's what it means. Here's a visual, physical interpretation. Here's a triple integral. Here's a physical interpretation, and so forth and so on for most of our ideas. This one is slightly trickier to have a physical interpretation of, but here let's give it let's give it an attempt here. All right, so here I have a surface. It's my surface S, and I have a vector n, and I have a boundary C, which is oriented counterclockwise relative to that n. Okay, so what about it? All right, so let's take a point on this surface. It doesn't matter what point it is, but I'm going to label it. I'm going to call this x naught, comma y naught, comma z naught. Now take a little circle, a very, very tiny circle. That's a little patch of surface area. So here I'm going to call that little circle S sub epsilon. I had a similar notation in a previous section, and all that means is it's a little bit of surface area that goes out a tiny epsilon amount. Here, the distance from x naught, comma y naught, comma z naught to the outer edge of that circle is meant to be epsilon. It's meant to be very, very small. Now, that little tiny patch, we can also give it a little tiny contour. There's a little boundary, and here I'm even going to orient that one counterclockwise. So here, that S sub epsilon, that's a surface area, right? That's a little tiny patch of surface area. On the other hand, I'm going to call this one C epsilon, and that one's going to be a little tiny contour. Okay, so I'm using the same notation as usual. S is a surface and C is a contour, but the little epsilon just means, oh, and this is for that little tiny piece of the whole section. Now let's zoom in on that little circle, and remember that, so here we're going to go ahead and zoom in, and we're going to take a look at that circle really close up. Okay, now remember that this entire surface rests within a vector field. So here there's a bunch of vectors flowing through in whatever direction. All right, well then that means that, remember, a vector field means that at every point in this region I have some vector that is assigned to that point. All right? So imagine the vector that's assigned to some point on the outer edge of this circle. It's no particular vector. It's just a vector that is that is coming from the vector field. Yeah? It's one of these vectors that the vector field assigns. And here it would assign it to anywhere on this circle, and I'm just going to decide to pick this one. If I draw them all, it's going to get very, very noisy, and I'm trying to simplify stuff. Notice that this vector is not anything in particular with respect to this circle. However, there are two vectors that are special with respect to the outer edge of some curve, and those are the unit tangent vector and the unit normal vector. Okay. Now notice that if this was lined up with the unit tangent vector, it would travel sort of along the outside of this circle. What I mean by that is if these unit vectors are just arbitrary vectors, well then whatever, they're going through this circle. But if these vectors from F, if these vectors from my vector field were to line up with T, well then these vectors wouldn't go through my sphere or through my circle, my disk. They would go along my disk, because that's what the unit tangent vectors do. They go along the outer edge of my circle. Okay, well, obviously this one doesn't, and there's no reason why it should. Well, remember, every vector is made up of components. So even though this vector doesn't travel in the direction of T, some part of it does. Some component of F travels in the direction of T. And if we go all the way back to chapter 11, we see that that can be found by the dot product of these two vectors. So the amount of F that travels in the direction of T is given by the dot product of F with T. So here F dot T is the component, or I guess I should say the magnitude of the component of the component of F that travels along the edge of my little s sub epsilon, or in other words, it travels along c sub epsilon. Like that. So here, f dot t is the component of f, right? Now, obviously, not all of f is going to do that, but some component, the part that is going in that direction, does. So now, if you were to take every vector f that does that all the way around, if you were to say, okay, let me find this vector that starts at this point of my circle, and let me take this vector that starts at this point of my circle, and do that to all of them, and see how these vectors f line up with the tangent vectors around my circle, what that would do is it would tell me the tendency for the vector field to rotate around my circle. That is to say, if f always lines up with the tangent vectors, that means that this vector field has vectors which go around the outer edge of my circle. Now, even if they don't do exactly that, the closer these two are together, the bigger that sum will be. If I add up how much component I have here, and if I add up the component for this vector and the component for this vector, the bigger number I get, the closer f was to being lined up with t all the way around. Okay, so here what I want to do is I want to add up my f dot t's, and since I want to do it for an infinitesimally short distance, I'm going to do that as an integral. So here, the integral, I guess I can continue writing in red, the integral, the integral of f dot t ds, because here, ds, it's around the arc length of my circle. Here, this is little s. Remember, capital S is for surface area, Little s is for arc length. Here, arc length. Right? If it was a capital S, that would be surface area. Little s is for arc length. And this is along the arc length of this little contour, this c sub epsilon. Note that f dot t ds was another way of writing f dot dr. Because after all, that's what t is. This should be a vector. T is the unit tangent vector, which is found by taking the derivative of the position vector. All right? If this has been parameterized, the way I find t is by taking r prime over the magnitude of r prime. So r prime over the magnitude of r prime ds can just be written as the integral over c epsilon of f dot dr. All right? It's the differential of r because it's the derivative of r with respect to the variable of r. So here, that's by the chain rule, just the differential of r. Here, let me denote that here because recall t is equal to r prime of s over magnitude of r prime of s, like that. But given what we just said, what this adds up to is telling us what is the tendency for these vectors to rotate, for them to line up around the outside of this little circle. This is called the circulation of your vector field around your little circle. So this is called the circulation of the vector field of f around that little circle. That's c sub epsilon. Here I should probably label that. That's what that circle is, c sub epsilon. The bigger that number is, the more that lines up. The more my vectors actually perform that action of going right around my circle. Okay, so now consider the stuff on the inside of this circle, namely the disk, S epsilon. So C epsilon is this outer bound, S epsilon is all the stuff inside. Well, note that the curl of your vector field inside of S sub epsilon, inside this little disk, is essentially constant. You say, how is it constant again? Well, remember, the curl is simply given by the differential operator crossed with f. So it has to do with the derivatives of the components. Right? It has to do with the change over the different variables. But remember, this little disk is epsilon in radius. It's tiny. So the distance between here and here is practically zero. So that means that if you take this point here, or this point here, or this point here, or this point here, anywhere in this disk, they're all so close together that the curl of f at this point is essentially the same as the curl of f at this point is essentially the curl of f at this point. Because they're all so close together, their derivative doesn't have a chance to grow, or how to say this. It doesn't matter what the derivative is, because the difference between here and here is so close together that regardless of what the derivative is, if I'm plugging in 2 points to that derivative that are extremely close together, I'm going to get a result that's extremely close together. So here the curl of f inside of S sub epsilon is essentially zero. Oh, sorry, is essentially constant because the radius of S sub e, S sub epsilon is epsilon, which is very, very small. Okay, so the curl of f is essentially a constant, the number 12, the number 5, or whatever. Okay. From this, we can get that the curl of f dot n inside of S sub epsilon is also essentially constant. I feel like I'm misspelling essentially. Let's see, that's Essentially. There we go. That looks a little better. Essentially. Note that the curl of f dot n inside of s sub epsilon is also essentially constant. Because, well, let's see. These don't change much. And here, as long as I'm inside of this little disk, notice this little disk is basically flat. So is essentially constant because since the disk S sub epsilon is so small that it is basically flat, that it is mostly flat, right? It doesn't matter how curved this is. If you take a small enough little disk, it's flat. Then n varies almost none from one point to another. From one point in S sub epsilon to another. Right? This thing is flat, so the normal vector here is about the same as the normal vector over here, which is about the same as the normal vector over here. So it doesn't matter where I'm taking n, doesn't matter at what point, it's basically the same vector. So here, this isn't changing much, it's basically constant, and this isn't changing much, it's basically constant. So their product isn't going to be changing much either. It's essentially constant. So what that means is that, so on S sub epsilon, we get that the double integral over S sub epsilon of the curl of f dot n ds, well, that's basically a constant. And, well, I know when I take an integral with a constant here, I can just factor that out. So here, that's going to give me essentially, again, that's not exactly true, but it's more or less the curl of f dot n times the double integral over s sub epsilon ds. But notice, this right here is just the surface area of my little s sub epsilon. Right here, this is the area of my little s sub epsilon. You say, well, you said it's a surface area. Yeah, but this thing's basically flat. So when something's flat, the surface area is just the area. Oh, so that's just the area of a disk. So here, that's going to be, this is approximately that, or in other words, this is approximately the curl of f dot n ds, dot n times this integral with respect to the surface area, which is really just the area of this little tiny disk up here. And the area of a little tiny disk is pi times its radius squared. Here I said the radius is this little tiny, almost zero number, which we call epsilon. So here this is going to be pi times epsilon squared. Okay, so that is what the curl of f dot n ds is approximately the same as. Oh, but by Stoke's theorem, which unfortunately we can't really prove here, but by Stoke's theorem, this is exactly the same as this. All right, the line integral over c sub epsilon of f dot dr is the same as the double integral over se curl of f dot n ds. Okay, so by Stoke's theorem, the integral over c sub epsilon of f dot dr is equal to the integral over the surface s sub epsilon of the curl of f dot n ds. Or in other words, this thing right here is the circulation of f around c epsilon, and that's going to equal to, or at least approximately equal to, because over here we made an approximation, is going to equal to the curl of f dot n times pi epsilon squared. But if I divide this over to the other side, this gives us the physical interpretation of what the curl is. The curl of f dot n is equal to the circulation, the tendency for my vector field to want to go around this little loop, the circulation of f around c sub epsilon, divided by, well, that's just the area of the little disk. This is the area inside of s sub epsilon. In physics, this is called the rate of circulation. The tendency for your vectors to go around the outer edge of your circle divided by the area inside your circle. Now keep in mind this all is an approximation, but these approximations can all be made better and better. Here I should write that with a curly equal sign because these are all approximations. But if we now take the limit as epsilon shrinks down to 0, then we can write as epsilon shrinks to 0, the approximation approaches the result. The smaller epsilon is, the better the approximation is, until the point where it's no longer an approximation. So that gives us that the curl of f dot n is equal to, that's going to be the circulation of f around c sub epsilon, but as epsilon goes to 0, that's going to be around every point of my curve. Or in other words, as we saw at the beginning, that's denoted as the line integral over c of f dot t ds. Here, that's just the area of your little circle, which is given by, what did we have? No, actually, we can write that as a limit. Let's go ahead and write that as the limit as epsilon approaches 0 of, and here we'll just write that as an area, 1 over pi epsilon squared. So here, as you take your limit, you end up with 1 over pi epsilon squared of the integral of c sub epsilon, that little tiny circle around the outside of your little tiny disk, of f dot t ds. All right? So here, this approximation is actually going to give you exactly this result, where this is called the rotation of f around n. Keep in mind this is a pointwise measure, so for any point x, y, z on our surface, the curl of f at that point, x naught, or x comma y comma z, dot the unit normal vector at that point is the rotation of your vector field around that point. Is the rotation of f about the unit normal vector at that point. F about n at x comma y comma z. So you give me a surface, you give me a point, and then figure out what the normal vector is at that point. Okay? Now take a vector field and pass it through here. That curl of f dot n tells me the tendency for that vector field to want to rotate around the line in the direction of the vector n. So here it gives me the tendency to want to rotate around here. Now keep in mind, this is for a single little point at a, this is at a single point surrounded by a little tiny circle around that point. But now if you add them all together, if you were to say, okay, now take this one, and then also this one with its normal vector, and then this one with its normal vector, and this one with its normal vector, and you wanted to add them all up. And if you wanted to do all of this, what Stokes' theorem essentially says is the double integral over S of the curl of f dot n ds. This is the cumulative rotations of around each point. So this is the cumulative tendency of rotation. Oh, what's the tendency for this for my vector field to want to rotate around this point? What's the tendency for my vector field to want to rotate around this point? What's the tendency for my vector field to want to rotate around this point? Okay, do it for every point and add them all together. Stokes' theorem says that that's the same as the line integral over C of f dot dr, or in other words, for the tendency of our vector field to want to rotate around the outer edge. All right, C after all is the outer edge, so that's going to, the cumulative tendency of rotation around each point, cumulative being the sum, right, of our surface is equal to the tendency for our vector field to rotate around the outer boundary of the surface. What happens in here adds up and ends up affecting what happens on the outer boundary. And when we say it like that, it makes just a little more physical sense. At least we hope. So as our last example for this section, a single application. Oh, let's see here. A single application. We have a vat of liquid, water or something, and due to certain forces, the liquid in here is rotating. It's going around and around and around. Okay, the liquid is swirling around a cylindrical container. Here, the radius of this container from here outwards is 2 meters in every direction. Here, you can even imagine you have a coordinate axis, so x and y and z. Okay? And the motion is described by a vector field. So here we're looking at the velocity of the particles of water on the surface of that container, and the vector field that governs the speed of the particles on the surface is given by f of x comma y comma z, and that's equal to negative y square root of x squared plus y squared comma x square root of x squared plus y squared comma 0. Okay. So here, obviously, this liquid is only rotating around the top layer. It's not rotating up and down. So here, that third component is just 0. And now the question is to find the double integral over S of the curl of f dot n ds, where S is the upper surface of this container, where S is the upper surface of the container. Okay. here the vector field is the velocity of water particles at the surface. Okay, so first of all, let's compute our curl. The curl of f, let's see here, that's going to be I, J, K, I, J, K, del x, del y, del z, del x, del y, and del z. And then my components here are going to be minus y square root of x squared plus y squared. Here I'm going to have x square root of x squared plus y squared. And here that's going to be 0. And same thing over here. Y square root of x squared plus y squared. X square root of x squared plus y squared. And 0. And now if I take the derivative of this with respect to x, seems to be all over the place here. So let's see, that's going to give us the derivative of 0 with respect to y, which is 0i. The derivative with respect to z of something that has no z in it, well, that's going to be 0j. And then with respect to k, I want to take the derivative of x square root of x squared plus y squared with respect to x. So that's going to use the product rule. The derivative of x is 1 times that square root plus the derivative of the second part times that x. So let me write the x first. The derivative of this part is going to be 1 over 2 square root of x squared plus y squared. The derivative of a square root is 1 over 2 square root. But then the chain rule says to multiply by the derivative of the inside. So that'll be 2x. And here these 2's drop out. Now minus, and I'm going to go the other direction here. That's going to give me the derivative of this, which doesn't have a z in it, with respect to z. So that'll just be 0i. The derivative with respect to anything of 0 is going to be 0. So that's 0j. Plus, and then k, well, I notice that's pretty much the same thing as the previous one, right? But now with respect to y. So the derivative of the first part is going to be minus 1 times that square root plus the derivative of the second part times the first. So that's going to be that negative y times 1 over 2 square root of x squared plus y squared. But then the chain rule has us multiply by the derivative with respect to y of x squared plus y squared, which is 2y. And again, these 2's divide out. So here the curl of f is going to be, let's see, 0 minus 0, that's just 0. 0 minus 0, that's just 0. And now here, let's go ahead and subtract these. That's going to be square root of x squared plus y squared plus, here's x squared over x squared plus y squared under a square root. Minus a minus, so all this becomes plus. So that's going to become plus the square root of x squared plus y squared. And then again, that's plus y squared over the square root of x squared plus y squared. Here, if I combine these two, in fact, I can combine these two. That's going to give me double the square root of x squared plus y squared. That one plus that one go there. These two have a common denominator, so I can add those. And that'll be x squared plus y squared over the square root of x squared plus y squared. And here, if I rationalize my denominator, it turns out that I have one more of the same kind. Namely, if I multiply top and bottom by the square root of x squared plus y squared, here, this is square root of x squared plus y squared times another square root of x squared plus y squared. It's just x squared plus y squared, which divides that x squared plus y squared. So here I have 2 square root of x squared plus y squared plus another square root of x squared plus y squared is 3 square root of x squared plus y squared. And that's our third component, 3 square root of x squared plus y squared. Just like that. So now we have our curl. So now we can go ahead and find the double integral over S of the curl of f dot n ds, because that's going to be the double integral over S of, well, I know my curl, that's 0, comma, 0, comma, 3 square root of x squared plus y squared. And then n, now remember n is the normal vector oriented upwards here. Right? Remember, this is perfectly flat. So the unit normal vector, which is keeping all of these oriented counterclockwise, is just the unit normal vector pointed straight up. Or in other words, it's the vector 0, comma, 0, comma, 1. Right? So normally we have to work for our 0 vector, but here this is a perfectly flat pool, which means the unit normal vector is going to be the same at every possible point. And it's going to be the unit vector pointed perpendicular to a flat plane, which is the unit vector pointed straight up. So here that's going to be 0, comma, 0, comma, 1, like that. The unit normal vector pointed straight up. Okay, so this is going to be the double integral over S. That's 0 times 0 plus 0 times 0 plus this times 1. Well, that's just going to be this. 3 times the square root of x squared plus y squared ds. Okay? So now, this is a, where am I here? This is simply going to be a surface integral over this surface. But notice this surface is just a flat disk. So here we could say, okay, that's the double integral over a surface area, but that surface area is just the area of a disk. So here we can more simply say, oh, that's equal to the double integral over a disk, and here I'll call that, I guess, d, 3 square root of x squared plus y squared dA for area. Okay, so now let's go ahead and integrate that. I notice I have the sum of squares inside a square root, which is going to make integration unpleasant. And I notice that my disk is, in fact, it's a disk, it's a circle. So here I think polar is the right way to go here. We can go ahead and change this. We want the whole circle. It's got a radius of 2 meters here. So we can have that describe dr d theta. R's boundaries are from 0 to 2, and since we want to go all the way around the pool, that means theta should go from 0 to 2 pi. Here that's going to be a 3, which let me go and kick that to the outside. There's a 3 out here. Square root of x squared plus y squared is the same as the square root of r squared. And don't forget, whenever you're changing from rectangular to polar, there is an extra factor of r. So here that's going to be 3 times the integral from 0 to 2 pi of the integral from 0 to 2. That's just r times another r is r squared dr d theta. And now we can integrate that really rather nicely. If we integrate this with respect to r, that's going to be 3 integral from 0 to 2 pi of r to the third over 3. Oh, I should have kept that 3 in there, right? Well, I suppose it's not too, well, yeah, let's just do it like that. Integrate from 0 up to 2 d theta. Right. Here, let's go and kick that 3 out there. So that's just going to be the integral from 0 to 2 pi of r to the third from 0 to 2. All right, take that 1/3 out. So now I'm just left with that numerator evaluated from 0 to 2. And that's going to be the integral from 0 to 2 pi of, if I evaluate this at 0, I get 0. But if I evaluate this at 2, I get 2 to the third, which is just 8. And now, finally, I can integrate with respect to theta, which will make that 8 theta from 0 to 2 pi. 8 times 0 is 0, so we don't care. But 8 times 2 pi is 16 pi. Just like that. And so that number represents the rotational tendency of this entire system. All right? There's more rotation happening on the outer edges than there is in the middle. there's a faster velocity versus a slower velocity, but taken as an entire system, this quantifies the rotational tendencies of the surface of this water. All right? And that is the end of our section. Okay? Note that if this curl is equal to 0 at the very beginning, if curl of f is equal to 0, well, let's see here. Note, if the curl of f is equal to 0, or I guess the 0 vector, then the double integral over s of the curl of f dot n ds is equal to 0 for all surfaces, for all s. All right? So if this is 0, then the double integral has to be 0. If we go back to section 5.1, where we first defined what the curl is, we had a name for a vector field whose curl was 0. It was called an irrotational vector field. Recall that if the curl of f is equal to the 0 vector, then f, the vector field, is called irrotational. Why? Well, now it makes a lot of sense. If the curl of f is 0, that means this double integral is equal to 0. But then that means that there's no rotation, there's no tendency to rotate around the points of your vector field. The vector field doesn't have a tendency to rotate around the points of a surface. And it doesn't matter what surface it is. Oh, and that must mean that the vector field has no rotational tendency at all. It is irrotational. It does not rotate. So that wraps up our application of curl, and hopefully this gives you a better understanding as to the physical nature of all of these computations. As an exercise for this section, you might wish to try section 15.8, problems 7 through 17 odd. And that should suffice. If anybody has any questions, any comments, any problems, please make a note of them and reach out to me, and I will get back to you as I can. All right? I hope everyone has a nice day.